Yeah, thank you very much for the kind introduction, and good morning, everyone. First of all, I would like to thank the organizers for the invitation and to give me a chance to present our results here during this nice workshop. Today I will come back from, in this second talk, I will come back from antiferromagnets to ferromagnets or ferrimagnet, which is Ig, and I would like to present you some interesting effects which we found, and we call this magnetoelastic boson accumulation. Already yesterday, in nice talk from Kashan, we already heard about interesting effects which can appear if you consider anti-crossing between magnons and phonons, and this is one of the effects which happens exactly in that region. So I would like to acknowledge also financial agencies which make possible this work, and also I would like to present you team who was involved in this. So these experiments were initiated by Professor Milkov from Kiev, and experimental work has been done in a group of Professor Hillebrands in Kaiserslautern, and theoretical explanation and simulation were done in collaboration with Professor Lvov and Dr. Anna Pomelo. Okay, let's start, and I will talk about yttrium iron garnet, nowadays well-known material. When I started as a student, I think only a few groups in the world were dealing with Ig, and if you present during the conference that you measure something in Ig, nobody understood at that time what is that material. But nevertheless, Professor Lvov and co-authors in their saga of Ig told that yttrium iron garnet is a marvel of nature, and its role in physics of magnets is analogous to that of germanium in semiconductor physics, water in hydrodynamics, and quartz in crystal acoustics. So you have seen already a few times these pictures. This is really unique material, and we are interested in this because of unique properties. Relatively high Curie temperature, and what is the most important for our BLS measurements is longest known magnon lifetime, as can be up to 1 microsecond, can reach 1 microsecond. And also it has very low phonon damping, which is smaller for quartz. Usually we are dealing with single crystal Ig films. Here you see some examples, and this is important for us because they are not green, as you can see here, but they are semi-transparent, and which is very important for our experiments with BLS if you would like to access, let's say, a little bit of volume of this material. So for the bulk crystal, basically no chance to access volume. It's too dark for light we use. So we use green laser light. So actually we are dealing with single crystal Ig films. And another reason why we, yeah.
So this question. So this Ig is known for very low damping and longest lifetime for magnons.
Right.
Is there any some reason for that? Is just accidental, or there is?
I think that it was found to some extent accidentally. This material does not exist in nature, so it was established, and I think in 60s or in the end of 50s. So people tried different combinations. You know that there is not only yttrium iron garnet, but instead of yttrium, people use all varieties of rare earth materials, and all of them were measured, and only this one exhibit the lowest known damping. So I think to some extent it was just luck. that we got that material. Okay, so reason why we also interested in thin films, I mean, in our case, thin means a few microns, because of rich spectra of spin waves in such geometry. So here I would like to talk about spin waves, about quanta of spin waves, magnons. They have, as you know, quadratic spectrum for in exchange regime. So they have momentum, also effective mass, where exchange constant is important. As you know, magnons carry spin of 1, and especially in IC, a lot of nonlinear effects take place. But what is the most important, that they take place at relatively low power. So sometimes power of a few microwatts is already enough to have nonlinearity. And thermally excited spin waves, we have something like 10 to the power 22 magnons per cubic centimeter at room temperature. So these are properties of spin waves. Let's go to the magnon spectrum, and it's, as I told you, it's very rich and complicated. But nowadays, I think, especially here, we understand this pretty good. So we here in this 2D plot, we show two directions. For example, perpendicular direction to the magnetic field. So magnons which propagate in perpendicular direction, magnons which propagate along the magnetic field. And as you can see, for a 6-micron IC film, it's pretty dense spectrum with characteristic minimum at non-zero k vectors, approximately 510 to the power 4 radian per centimeters. And in the exchange regime for higher k vectors, I mean, the spectrum is proportional to the squared wave vector number. This spectrum can be obtained from Landau-Lifshitz equation, taking into account effective field, which contains of different parts, like external field, which we can vary and shift the spectrum up and down. Then a dipolar field, exchange field, and all possible anisotropy field, and so on. So I would like to admit that for pure IC, let's say, anisotropy fields are relatively low if you compare with magnetization or with applied fields. So it's like 1 or 2, at least 1 order smaller, or even 2 orders smaller. So magnons, as I told you, are bosons, and they can be in thermal equilibrium, they can be described by Bose-Einstein distribution with zero chemical potential. But what is good, that we can pump a lot of magnons in our system, and in such case, we can utilize parametric pumping technique, which is basically nothing more like shaking our external field with double frequency, which is shown here. And what happens, actually for exchange, purely exchange spin waves, nothing should happen. But as you can see, that it's not that spin circulate not along the circle, but along the ellipse, and which is basically bended because of constant length of the magnetization vector. And then if we shake our field with double frequency, we basically couple to this double frequency component, and we amplify this, and then angle of the excitation starts to increase, and in such a way we basically create more and more magnets, which reduce this green vector, which is basically that component of the magnetization. So,
in the link, is there some specific phase relation that you have to fulfill running this process?
So about phase, I will talk maybe just right now. So the same process you can imagine in the quasi-particle, let's say, picture. So if you have one photon with omega with F pumping, it's split to two magnons with at half of the pumping frequency to fulfill energy conservation law, this one, and also practically opposite k vector, since pumping wave vector is almost zero, and then we have basically plus and minus q of spin waves. And here, actually, if you look at the phase of these two spin waves, so these two magnons, and you sum up them, so you have phase of your pumping plus pi over 2. And this is a relation which is for every such single process splitting of one photon to two magnons is valid. So it means that sum of these phases of these two created magnons equal to the phase of pumping plus pi over 2, but not difference, unfortunately. Otherwise it would be directly, let's say, condensate with particular phase. So it means that if you have four magnons created in two processes, they are not necessarily they have not difference in phases is not necessarily the same, but sum is exactly is defined by pumping phase of the pumping field. So in such a way, principally what I can add a little bit from another experiment, in such a way, if you, for example, to somehow create one magnon with particular phase, then and make this process and parametrically create let's say the second one, if first one is somehow you have some seeding signal also with particular phase, so the phase of the second one will be, let's say, defined by the seeding signal here. So and this can be utilized for propagating spin waves, for example. So and you can see nice oscillation depending on the phase. Okay, so as you know, what happens further? So the thermalization process happens. So as I told, nonlinear effects here are pretty strong, and they, if you excite with parametric pumping something like 10 to the power 20 magnons per cubic centimeters, they basically immediately start to interact with each other and redistribute over the whole spectrum. And after some time, what you can observe, so as you know, chemical potential rises in such case, and if it reaches this minimal value, Bose-Einstein condensate of magnons establishes, and it was demonstrated some time ago. What is important, that demonstration of the Bose-Einstein condensate and all these measurements were done with Brilliant Light Scattering Spectroscopy, which is basically, was already explained a few times, I think. I will remind that it's inelastically scattering of the incident photon on magnon with creation or annihilation one magnon, so it depends Stokes or anti-Stokes process we have, and then scattered photon contains all information about that magnon. So it contains information about frequency, wavelength or wave vector, and also phase about that magnon. Question is how to detect this. So with frequency, everything is clear. Using Fabry-Perot interferometer, we just filter our scattered signal, and we see nice peaks from the left and right, like Stokes and anti-Stokes peaks, and we know frequency of the magnon. But if we measure close to the bottom, you see this region is pretty flat, and you measure different wave vectors. Since frequency resolution of the BLS technique is, let's say, 100 megahertz, it would be correct. Sometimes people report about 50 megahertz, but this is minimal value which I heard. So you still detect signal as in this peak you detect signal from broad range of the dispersion curve here. So it would be great if you would be able to somehow to access only some particular wave numbers, so to have wave number resolution, and it has been done in our group by Dima Boshko. So such setup was created, and as you can see, instead of shining light to the sample, we created a setup which can rotate, and we can shine, so we can send incident laser light from different directions, and basically detect in a backscattered light with the same setup. So as
a technical question.
Yes.
The mirror underneath is a dielectric mirror.
So it's not necessarily. In this experiment, which I will demonstrate, no, in the first experiment we simply had antenna, so microstrip antenna, which is metallic, under the sample, and it was enough reflection. So signal was poor, but still it was, you just wait longer time, and it was enough reflection back. So I have to explain a little bit. So if you send incident light under some angle, it has two components: horizontal, so let's say in plane of the sample, and vertical. So vertical. So you have to, in order to detect in the same way, you have to reflect both of these components. So vertical components will be reflected by mirror. So in our first cases, it was just metallic microstripe, and nowadays we use dielectric mirror. But horizontal component can be reflected, or after interaction with magnon with double wave vector, can be turned in the opposite direction. At the end, you have exactly the same direction of the scattered light, you see? So, and then this wave number of magnons can be easily found from the wave number of laser light, and sign of the angle, which is angle between normal to the plane, let's say, and our incident light. So this, you see, we can nicely change it from -90 to +90. In real experiments, it's not like that, so there are some limitations, but theoretically you can access such really already exchange region of the spin wave spectrum. With reasonable resolution, you see it's about 1% of that value. Okay, so let's see what we can gain out of this technique. So in the first experiments we published it in 2014, we applied some pumping pulse, which was like 1.5 microsecond long. And here you see a diagram, x-axis is time and y-axis is wave number. So we directly see what happens, so which magnons we see at different moment of time. So at the beginning, nothing happens here in this region where we can we can access magnons, because parametric pumping needs some time to develop, and thermalization should take place to that magnons from excited from the region where they excited parametrically should somehow appear here. Should appear here in this region where we measure. So therefore, the initial delay is here. And then you see the first magnons appear somewhere for high k vectors, like 10 to the power 5, and they relatively quickly thermalize down and around the minimum of the spectrum. And BSE is formed here. This was experiment with relatively narrow pumping area, around 50 micrometers. And what happens if we make it brighter? And then signal looks the same, basically experiment, but gives us completely different result. I mean, there is clear second area, so there is clear area around 8 to the power 4 with accumulation of magnons here. So this is bottom of the spectrum, so this point, and something here also happens, and the magnons accumulated on the way to the bottom. And this, we found that it coincides very well with the hybridization area with transversal phonon branch, which was already reported here. So if you compare, so it corresponds 1-to-1 without any parameters. We just took our magnetic field and calculated these two dispersions. And we call this magnetoelastic mode because clear that both magnetic and elastic energy interplay here. And
yeah. I don't quite understand the pumping area, right? So that's defined by the lithography of the antenna, or
exactly.
And the smaller one was 50 microns, right?
So here we have 550 microns, so 10 times smaller.
So I don't quite understand
why it happens.
At these wave vectors, why that makes a difference.
And so this I can this how we understand. Its reason is high group velocity at this cross section. So you can have states with relatively high group velocity here. Also, magnons here are relatively slow. You see, and this mode accumulates here. Simply, region is large, but the same mode can escape in the previous experiment. You see, almost nothing here is visible. Okay, practically nothing because region is too small. And if mode has high group velocity, it simply just escape of that region, and you do not detect it. You see? So this is our kind of naive explanation what is going on. Why here we see that signal, and there and for a small area not. About high group velocity, I will report at the end of my talk. So there are additional experiments and which directly show that group velocity is much higher than the group velocity of magnons around, because at the bottom we should have zero group velocity. They do not propagate. Yes.
In this experimental scheme, what is the time resolution, and what in the set of defined time resolution?
So time resolution basically can be very good, like 1 nanosecond. 1 nanosecond. I'm not sure that here time resolution was set for 1 nanosecond, because the reason is simple. You have to wait much longer to have in each your channel for each nanoseconds enough counts and enough to plot like this. So maybe here it was. I think that here we took some compromise because it's 1.5 microseconds. Maybe it was a resolution of a few nanoseconds, but something like that.
It's determined by the electronics.
It's determined by electronics. No. It's determined by electronics of BLS system.
And can you estimate the formation time of the BSC?
Formation time of BSC.
Or maybe, sorry, the question after you apply the PAM-PAS, is there a delay between application of PAM-PAS and establishment of BSC, or not?
So at least from this picture, you see that at least delay is a few hundred nanoseconds. You see that some signal starts to appear, and then I would say that BSC here is clear peak, because so I don't want to say that everything here is BSC, because you have normal magnons and normal phase around at neighboring branches and so on. So that's why to me it needs like for this this time depends on the applied parametric pumping power. So if we especially applied low power to see these dynamics. Otherwise, you see in this paper actually there are two pictures, and for high for the high parametric pumping, you see completely different picture, which was explained there. But yeah.
So for that pump pulse, the rise time is still important, right? That's your final resolution of the pulse.
So rise time of the pulses is around 5 nanoseconds. That's why it's not a question here. So it's comparable with the resolution of BLS setup here. Yeah. So that's why. But if you just imagine some experiment with longer rise time, so probably it would be important. But here it's not an issue.
So is it possible to, by either sweeping the field or going to a different orientation, to eliminate the pure magnon BEC, so you just isolate a magnon polar BEC? So basically this curve has like one minimum in the magnon polar. Right, this is the point, right, is that you have sort of two minima, right? One is the original minimum of the BEC. The other one is sort of this minimum created by, right, this magnon polar.
Yeah.
Is the idea. So is it possible just to use a parameter in the system and just have just a magnon polar BEC? Is that possible?
So first of all, it's possible to shift this magnetic field, this spectrum up and down of magnons. So then this point, cross-section point, will move how you want. So you can bring it to the same point or you can move it away. So, but to eliminate, how to say, this point, I do not know. I mean, you cannot eliminate, meaning you can just bring them together and maybe something interesting happens, but we have not measured yet in such regime. So, and also, in this paper, we claim that we see accumulation, but not so far not condensation of magnons, because it should be proven that phase of these magnons is the same, you know, that it's condensed state. So it's not that trivial task. So yeah, at this moment we see only accumulation here. So let's go further, and I will try to explain how.
Sorry. On this time graph, you turn on the pulse and then you turn it off at one point.
Right.
You're turning it on and off. So the BEC red part comes on when the pulse is on, and then you turn it off.
Yes, it appears here after.
So are you turning off the pulse at one point?
Yes. So at this point, so pumping pulse is this one you see, and it is turning off here.
Okay, the red thing is where you turn off.
Yes.
Okay, but why doesn't the BEC continue to form while the pulse is on?
This is basically was investigation. So task for an explanation in this paper, and it was explained in the following way. So with strong power, by the way, you see that here we used 40 watts. So if you use 40 watts for narrow pumping region, so you basically see something very gray area here, but not a lot of magnons, I would say. And then if you turn off your pumping pulse, you see strong peak at the bottom, which is can be 5 times higher than during the pumping pulse. And our explanation is the following: that with strong pumping power, you overheat the bottom of your spectrum. And if you and it was proposed by Slavin and Tiberkevich, our collaborators from USA, that we have kind of evaporation process. So if magnons from this overheated area escape so they due to the, for example, four-magnon interaction, they go to the higher energies, and they kind of cool that bottom area, and you have kind of evaporation process, and effective temperature cools down relatively quickly, and then in this moment BEC is formed, because during the pumping pulse, effective let's say magnon temperature in that area only at low frequencies, like let's say around 10 gigahertz or so, is strongly overheated. So you simply pump too many magnon. And this process helps us to form BEC afterwards. And this was actually, it was reported here. So if you apply smaller, actually it was hard to find this such tiny range of pumping powers where you see strong signal at the bottom, because or you do not reach that threshold, or you already overheat. So this only, let's say, there is some power where you see signal during the pulse, let's say. But I assume that in this case, spectrum here is not overheated. So let's say magnon temperature is relatively low. But magnon temperature for strong power was, in that paper, was estimated like 30,000 Kelvin or something like that. So yeah, it's not real temperature, of course, but it's just how you can describe distribution, which you after you pumped a lot of magnons. Okay, so let's go to the explanation of this strange accumulation. So why these quasi-particles? So we call them magnetoelastic bosons or magnetoelastic mode quasi-particles. Why they accumulate there? And what is important to know that this accumulation takes place before signal at the bottom is measured. So you see that there is time shift between these two peaks, let's say. So here we did a little bit more experiments. Here you see basically BLS frequency as a function of the wave vector. So this is in-plane wave vector, where we can access, and so no time resolution anymore. But what is visible that, first of all, this, even for low powers, this peak, magnetoelastic peak is visible. And second is that magnons appears in this measuring area from the right side. It means they appear from the exchange region. So thermalization somehow prefers, so they prefer to go along the lowest mode, or along. So okay, the concentration of mode here is pretty high, but along this way. So they prefer not here somehow, but from the exchange region. And then if we increase our pumping power for the same wide pumping region, 500 micrometers, you see clearly that this peak increases, but also at some point signal at the bottom is formed. And then we have such nice picture for 12.3 watts, that strong signal already at the bottom, but even stronger signal in the point of cross section. And at some point it saturates. So you see between 12 watts and 40 watts, we have almost the same peak at the crossing point, and but BSC increases, and it basically it should increase with increasing of power to some value. Okay, so let's look on this area a little bit closer. So what we have, we call this effect of accumulation magnon bottleneck accumulation of magnon-phonon high bosons. And why bottleneck? Because if you calculate ratio between, so if you look on these two branches, which now contains phonons and magnons, so it's not anymore only magnon, but here it's magnons and then it's phonons. So this branch, let's say upper branch and lower branch. So even in the point of minimum here, so the magnon, so magnetic energy is higher than elastic energy in this point. So it's still quasi-particle here contains magnetic energy, which is higher than elastic. So therefore, this is not pure magnon, but nevertheless magnetic energy is present there. So what we have kind of bottleneck here. So magnons thermalize and propagate along this, how we call this, magnon highway, and then they have kind of barrier. They accumulate somewhere here. So in order to describe this, yes.
So why do you call one of them a condensate and not the other one?
So simply because for this BSC, by a group of Professor Demokritov in Münster, a special experiment was done, and they tried to measure phase of that, so to see phase of that condensate, and they were able to see clear phase picture with BLS measurements. So here, so far, so I don't want to say that this is not condensate. I would like to say that at this moment it's not known yet whether it's condensate or not. but because just to be fair, let's say. But obviously that we should try to check this. It's not that easy because here you sit in the minimum, and then your condensate does not propagate. So you have enough time to measure because BLS is time consuming. So you have enough time to measure. Here, obviously, you have to do something different, or maybe huge area like millimeters area. Try to pump or so, but you will see that they propagate pretty fast and they escape the region of pumping region pretty fast. So I will go to the most complicated for me part, which is a theoretical explanation, which was done by our collaborators. They used Hamiltonian approach. First, you see here A and B complex amplitudes for magnons and phonons, and Hamiltonian was one can write in this form that second order it contains magnons and phonons, omega m, omega p. It's dispersion for magnons and phonons. Here we have hybridization, so we have interaction between them with coupling constant delta, and also since the interaction between magnon-magnon interaction is much stronger than phonon-phonon interaction, so we include force this H4 only for magnons in these equations. So now we would like to diagonalize this.
Why is that because the 4 magnon processes are the dominant ones?
Yes. So right. For our case, basically 3 magnon process is prohibited because field is too high, and only 4 magnon. And let's say, you can include 2 magnon process, which always exist basically as soon as you have some impurities or something like imperfection in your crystal. But let's say as a first step, you can just take 4 magnon process in this explanation, and you will see that at least for the understanding of this experiment, it was enough. So probably it makes sense to. Then of course you can make next step and next. So very quickly here, so they then did Bogolubov transformation to the C plus and C minus in this form with parameter phi angle, which is kind of rotation in the AB plane. And here you see this O is difference between frequencies at particular wave vector and divided by delta. Capital omega here and there, plus and minus, are simply dispersion of the upper branch now. So we will come from dispersion for separate dispersions from magnon and phonon to dispersion upper branch, which was blue, and lower branch, which was green. So in this, so you can see here. So upper branch we call this with plus or U, and lower branch with minus. And in this case we have diagonal Hamiltonian, and this simple formula for the dispersions of these 2 branches. So the next step is to include interactions, and we consider 3 types of interactions. So interaction for upper branch, so inside of only here inside of this upper branch, inside of lower branch, and in between. And as you can see here, that interaction amplitude, these T parameters, they are large for, let's say, for magnons here and for magnons here, but they then decreases drastically if you go along this branch to phonons. This is what I just told, that interaction in phonon and nonlinearity in phonon system in IC is much weaker than that for magnons. And interaction amplitude, this cross upper lower interaction amplitude has form of peak, and with maximum in this crossing point, this virtual, let's say, crossing point. So, and here x is dimensionless distance to this crossover. So, and then using this, we continue with statistical description, and basically for 1D, for the we end up with balance equation where change of the normalized quantity of, so a normalized concentration of magnons in one branch, so which is green here, is basically change of the flux and minus the transition from the lower branch to upper branch. So let's say, so this describes basically the dynamics on this green lower branch. Here you can see proportionality of these two values to scattering amplitudes. Minus minus means the bottom branch, plus minus plus, or plus minus, it's in between these two branches. So here normalized amplitudes, we normalize on the high large values like plus 5 or so, so it's far away here. So this is n minus infinity, and minus for negative value, it's somewhere here. We basically took this quantity of magnons in the back state, so in the Bose-Einstein condensation state. And then if we put everything together, we have basically at the end relatively simple differential equation which can be solved, and solution looks like that, so that we are interested in the concentration, normalized concentration on this branch, and it depends on that on such parameter A, and basically this is a ratio between the quantity of magnons here and magnons here. So basically ratio between these two values. And it's clear then that if there are no condensed magnons, there are no magnons at the bottom, then this value is 0, and basically it means that all magnons which thermalize, so they continue to stay on this lower branch. They will not go there, and only if this value A is finite, small but finite, there is clear peak. Basically, I have to explain. So this 0 means basically virtual cross-section point here, and negative values, it means that we are staying somewhere on this green, you see, on this green branch, lower branch, but somewhere here to the left part from this crossover. That's why this is negative. So therefore, it's clear that if we have some finite value of the in BSE state or magnons over there, so then we will form, you see, we will form peak, and which basically we see due to the bottleneck. So magnons propagate here, and then not all of them can simply come from scatter from lower branch to upper branch to form BSE here. So they basically stuck here, and then you can see if you will have more and more magnons here, this accumulation, at least in numerical simulation, decreases and can be very, very weak. But I have to say that this basically explains saturation of that peak, at least qualitatively. So basically, as soon as you have here more magnons, then basically this peak does not increase anymore, but basically saturate to some value. Okay, so and the last two slides about transport. So this, as I told you, here you see group velocities and the same dispersion for this cross-section region. And what we did, basically, we did time and space scan of our sample. And if we stay in this at the bottom, if you look at the bottom, it is these k vectors, we see clearly that signal during the time basically does not propagate as it should be. So BSE does not propagate, and basically all magnons are here in normal phase, in BSE phase. they do not propagate and they stay close to the pumping region basically and attenuate later. But for the K vectors around cross-section region, clear propagation is visible. You see this basically is space and this is time, so slope basically gives you group velocity directly from these measurements. And there are two of them, these two group velocity. Point 1 just demonstrates that this group velocity like around 200 meters per second, which is basically here in on this this lower range. And there is also second one which is much higher, around 100 meters per second, which is basically very close to that minima. So we believe that this is second one is that signal which we see as accumulated signal close to the cross section. So, and as you can see, it escape region of pumping. So pumping region is, is it micrometer? No, pumping region is larger here, but if it's, let's say, only 50 micron, then you have no chance to see that signal. It simply escape that region. So here it's plus, so it's here, as you see, 300 micrometers, so which is within our area. So with this, I would like to finalize my talk. And so you have seen that we observed bottleneck accumulation of hybrid magnetoelastic bosons, developed a minimal model which qualitatively describes this effect, and you can use these quasi-particles for spin transport since they possess non-zero group velocity. So with this, also I would like to admit that these kind of effects can occur in any multi-component gas mixture with different scattering amplitudes for different components. So, and with this, I would like to thank for your attention.